mathematicians. Today we see a nice problem about Jordan canonical form asked in NBHM PhD 2020. It is a very important problem. It can be asked again also in various exams. Let T be a linear operator and the vector space R power 5. Therefore, if you look at the matrix of this linear operator, it will be a 5 by 5 matrix. It is given that it is nilpotent. It means that T power n is equal to 0 for some n, and we are defining di to be dimension of the kernel of t power I. Okay, this has a name, so we call nullity. What is the meaning of nullity of a matrix A? This is the dimension of kernel of A. Okay, so this d1 is the it's a nullity of t, d2 is the nullity of t square, d3 is the nullity of t cube. Okay, then we are given four options. Which of the following can possibly occur as a value of d1, d2, d3? That is the question. So let's see how to approach this problem. So this problem uses Jordan canonical form. Okay, so Jordan canonical form is a very important concept for competitive exams. And not just this problem, you can solve many problems related to diagonalizability also using Jordan canonical forms. Okay, so I have made two videos regarding Jordan canonical form. One more video I will upload on Jordan canonical form. So first you can check these two videos. The advantage of learning Jordan canonical form is you can solve any problem related to diagonalizable matrices also in a much simpler way using Jordan canonical form. Okay, so you can check that videos. It will improve your understanding regarding diagonalizability of matrices. Okay, so let's proceed on this problem. So let A be the matrix of T. Okay, so it is given that T is nilpotent, therefore A will be a nilpotent matrix. Now, since A is a nilpotent matrix, by Jordan canonical form theorem, A is similar to a Jordan matrix, in which, so if it is a Jordan matrix, the diagonals are Jordan blocks. Everywhere else it is 0. So now what is a Jordan block? So it is a nilpotent matrix, so all the eigenvalues are 0. Therefore, all the Jordan blocks are corresponds to the eigenvalue 0. Now, suppose I will give an example of suppose n2 is 5 by 5. I will give an example of a 5 by 5 Jordan block corresponds to the eigenvalue 0. This is an example. So, this is a 5 by 5 Jordan block corresponds to the eigenvalue 0. So, yeah, if it is an arbitrary eigenvalue lambda, then you will have in the diagonal you will have lambda. Okay, since we have this is 0, in the diagonal we are getting 0, but usually Jordan block is just a upper triangular matrix and the diagonals are the eigenvalue that it corresponds to. Then above this, above the main diagonal, this is called super diagonal. In this super diagonal, all the entries should be 1. That is a very important condition. Okay, so if it is a 5 by 5 block, then in the super diagonal there will be 4 ones, and everywhere else it is 0. Okay, since it is corresponds to 0, we are getting all the diagonals are 0. If it is corresponds, if it is a Jordan block corresponds to an eigenvalue lambda, then all the diagonal entries in will be that lambda. Okay, so that is what Jordan block is. And if it is a Jordan matrix, then it is a diagonal. It is a diagonal block matrix in which each diagonal blocks are Jordan blocks. So with this understanding, we try to answer this question. So A is a 5 by 5 matrix. Therefore, the sum of these blocks, sum of the sizes of the blocks should be equal to 5. Okay, for example, this is a 2 by 2 block, 2 by 2 block. This can be a 1 by 1 block, and so on. So now we want to understand the nullity of A square and A cube. So note that finding the square of A is same as, so you can just find the square of each of the diagonal blocks and you put it in as a diagonal form. So that is the uh, that is a simple result to observe. So to understand the nullity of A square, we want to understand the nullity of power of a Jordan block. Okay, so that is our next observation. So these are some important results. These results are proved in my videos, Jordan canonical form 1 and 2. You can check the description. So nullity of A is equal to number of Jordan blocks. So that is our first result. So for example, this there are k Jordan blocks here. That means that for this matrix A, the nullity is k. Okay. Now as I said, we want to understand the powers of a Jordan block. So this is a 5 by 5 Jordan block corresponds to the eigenvalue 0. If we calculate the squares, what happens is these ones is shifted one step above. So, okay, it goes here. And if you calculate one more power 3, these ones will go two step above. It will go here. If you calculate the power 4, these ones will go here. And if you calculate power 5, this one will go outside. Means everything it will be a zero matrix. Okay. So, so we note that at each step these ones are going up, up, up. That means that at each step nullity is increasing by one. Okay, first you see from here to here, you got one more uh, row becomes zero. When this once goes here, you will get this third row also becomes zero. So likewise, when you calculate the powers of a Jordan block, each step you will get a new zero row, therefore nullity will be increased by 1 at each step. Okay, so this will, okay, here we make one minor observation. So this is a 5 by 5 block, 5 by 5 Jordan block, because it is a, it has four ones. What is a 1 by 1 Jordan block corresponds to 0? This is this block, just 0. Okay, so this is 1 by 1 Jordan block corresponds to the eigenvalue 0. If you calculate the power of this Jordan block, it remains itself. Okay, so if it is a Jordan block of size greater than or equal to 2, for example, if it is a size 2 Jordan block, what will you get? So this is the 0 1 0 0. This is the size 2 Jordan block. If you calculate its power, second power, you will get 0 0 0 0. So in particular, even if it is a size 2 block, you are getting one more, that nullity is increased by 1. Here nullity is 1, but here nullity is 2. But if it is a size 1 block, then by when you calculate its power, nullity will not increase. Nullity remains same. So that is one minor observation. So it is not true that for every power of Jordan block, the power is going to increase. No. So if it is a block of size at least 2, then the size will go to increase by 1 at each step. So now what happens here is, so we have A. So we assume that all of these blocks are of size at least 2. Okay. When you calculate A square, what happens is, here nullity will increase 1, here nullity will increase 1, here nullity will increase 1. Therefore in A square you will have yet k many k row new rows are made 0. Therefore nullity of A square will be nullity of A plus nullity plus k, where k is the number of Jordan blocks of size at least 2. Okay, if there are size 1 blocks, you don't consider them, just count the number of Jordan blocks of size at least 2, and each of them the nullity will increase 1. Therefore nullity of A square will be nullity of A plus number of Jordan blocks of size at least 2. With this observation, we answer the problem. So it is given that D1 equal to 1, D2 equal to 2, D3 equal to 3. This means that nullity of A is 1, A square is 2, A square, A cube is 3. So nullity of A equal to 1 means there is only one block in the Jordan canonical form of the matrix A. But the A and the Jordan canonical form are similar matrices. Similar matrices have the same nullity. So we very well assume that A itself is a Jordan canonical. A itself is a Jordan matrix, right? So we get A is this Jordan block because nullity of A is 1. So we saw that if so it is a 5 by 5 block. So and so if it is size at least 2, then in the A square nullity will be increased by 1, and A cube nullity will be further increased by 1. Okay, so that we, for this matrix we already saw these ones are going to shift above and above for each step. So we see that nullity of A is 1 means nullity of A square is 2, A cube is 3. Therefore this is possible. Therefore this is true. Let's go to 235. Now nullity of A is 2. Therefore the Jordan canonical form of A will have two Jordan blocks. So it is A is a 5 by 5 matrix. This is two blocks, means there are two possibilities. This is a 3 block and this is a 2 block. 3 block and a 2 block, or this is a 4 block and it is a 1 block. Okay. Now we look at suppose this case 3 block and 1 block 2 block. Now in this case each of the block has size at least 2. Therefore in the nullity of A square dimension will be nullity will be increased to 1 for each block. So we get 2 the nullity of A plus 2 which we got from these two blocks. So nullity of A square is 4 in this case. Now we come to this case. So it is a 4 block and 1 block. So it will be like this. This is a 4 block and a 1 block. Now see, this 1 block won't contribute to the nullity because it is 1 block. So only this block will contribute to nullity. So when you calculate square, this block will increase the nullity by 1. That's it. Therefore, nullity of A square will be, so in this case, nullity of A square is 4, and in this case, we get nullity of A square will be 3. Okay. So now in this case, when you calculate A cube, in this case, when you calculate A cube, again nullity will increase one more. So you get nullity of A cube will be 4. Okay. So we get the answer. In this case, the nullity will be like 2 and then 3 and then 4. Okay, because like when you calculate cube, these ones will go one more step, and this 0 is not going to contribute to uh, any new nullity in the powers. So if for this partition the associated nullity sequence is 2 3 4, in this case what happens is, so already we got I mean this is of the form 2 comma 4 comma, let's not worry about what going to come here. So you see that this option is 2 3 5, but here we got 2 3 4, here we got 2 4, already it is not matching, okay, with the first two terms. Therefore this sequence is not possible. Okay. Okay, so let's continue in the next option. 2 2 4 is not possible. We just saw that in, if it is a nullity of A is 2, then the second the nullity of A square is either 3 or 4. Okay. Therefore, this 2 cannot occur because in the next step definitely nullity will increase because of the blocks. So this is not possible. And 2 4 5. So for 2 4 5 we take the partition n1 equal to 3 and n2 equal to 2. So we look at this partition, we understand what is this number now. So this is a 3 block and this is a 2 block. When you calculate the power, what happens? Nullity will increase 1 here, nullity will increase 1 here. So we get nullity of, so we already saw that nullity of A square is 4 and nullity of A is 2. When you calculate, when you multiply A with this A square, so we get A cube. What happens is, uh, this block become 0. So you can multiply these two matrices A and A square. You will see that A cube will be 0 matrix. That means the nullity of A power 5 is 5. Therefore 2 4 5 is indeed possible. Okay. Therefore we have solved all the 4 options. Now we'll look at how to solve this problem in generally. So what we have understood is, if you look at a Jordan matrix, if the size of you, so some blocks might have size 1, some, so that will not give new nullity to the higher powers, but if the blocks of size 2, they will give size blocks of size at least 2, each of them will give one nullity to the square of the matrix. Therefore so nullity of A square equal to nullity of A plus number of Jordan blocks of size at least 2. So by using that we can in general solve this problem. So let's see how to do it. So consider n by n nilpotent matrix such that A power m equal to 0. I take di to be the nullity of the matrix A power I, and A power m equal to 0, and so I look at the nullity of A square up to A power m. Okay, since A power m equal to 0, nullity of A power m will be n. Now, so the Jordan canonical form of A will have D1 blocks because D1 is the nullity of A. So we D1 I simply I denote it by K. So K equal to D1. So we get this K blocks J n1 of 0, J up to J n K of 0. Okay. Now if this is so we saw that if the some block is 1, then that block won't contribute to the nullity of the higher powers. Okay, so that we already observed. Therefore, D2 nullity of A square equal to nullity of A1 plus number of blocks whose whose size is at least 2. This is a formula. Again, suppose like suppose n1 equal to 2. So first block is a 2 by 2 block. Then in A square, this block becomes 0 block. Okay, so note that if it is a 2 by 2 block, when you calculate the power, it becomes 0. So after that, when you calculate A cube, this block will not give you any new nullity to A cube. Therefore, we make a very important observation here. Therefore, therefore, nullity of A cube is nullity of A2 plus number of blocks in A, number of Jordan blocks in A whose dimension is at least 3. Okay, if it is has dimension 3, then when it go to A square, it will be a 2 by 2 kind of block. So so that block will not become 0 if it is a block of size at least 3. When you look at the same block in A square, that block will not become 0. Therefore, in the next step also it will contribute to the nullity. Therefore, we get nullity of A cube equal to nullity of A square plus number of blocks in A. You note that this NIs are sizes of the blocks in the matrix A. Okay. So, we get D3 equal to D2 plus number of blocks of size uh, at least 3 in A or size at least 2 in A square. I think this we don't need. This we might make some confusion. So D3 equal to D2 plus number of blocks in the A of size at least 3. So this with this observation we can solve this problem to even arbitrary case for any numbers. Okay. Now so we deal with only nilpotent matrices, but maybe in the next time exam they might ask for arbitrary matrices. Okay, how to approach arbitrary matrix. Okay, so let's take a complex matrix. Okay, so to talk about Jordan canonical form, we want it all the eigenvalues to lie in the underlying field. Okay, so we take complex matrices so that the eigenvalues are in the field itself. So now we assume that lambda is not equal to 0 because if the eigenvalues are 0, then we know how to proceed. So we assume lambda not equal to 0 and we assume that all the eigenvalues of A are equal to lambda. Okay, so then the Jordan canonical form A will be equal to again diagonal block matrix where each diagonal block is a Jordan block corresponds to the eigenvalue lambda. So now corresponds to lambda means diagonals will be lambda, super diagonal will be 1, everywhere else it is 0. Okay, again now this for arbitrary lambda we saw that number of Jordan blocks is equal to nullity of A. That is for eigenvalue 0. When it comes to the non-zero eigenvalue, the number of Jordan blocks it is equal to geometric multiplicity of the eigenvalue lambda. Note that geometric multiplicity of 0 is the nullity of the matrix. Okay, so this value equal to nullity of A when lambda is 0. So now so this is one Jordan block. We look at J3 of lambda minus lambda I. Okay, so what happens? This all the diagonal lambda will get subtracted. We get this matrix, and this is a so there is a notation confusion. This is J uh, 3 of 0. This is the 3 by 3 Jordan block corresponds to the eigenvalue 0. So there is a relation between 3 by 3 by 3 Jordan block corresponds to lambda and 3 by 3 Jordan block corresponds to 0. Now let's define di to be geometric multiplicity of lambda in the matrix A power 5, A power I. Now the question is which d1, d2, 3 are possible. So whatever we did for 0, we trying to do for arbitrary eigenvalue lambda. Okay, now we just saw that j3 of lambda equal to so from this equation we get jm of lambda equal to jm of 0 plus lambda I. So this lambda I we can push it this side. So we want to understand again the powers of Jordan blocks. Okay, so now, so this power L will be this power L. Note that this lambda is a scalar matrix. Scalar matrix commutes with all the matrices. So whenever two matrices commutes, we can expand them in the binomial theorem. Okay, so Jm of lambda whole power L is equal to summation L I equal to 0 to L. Lambda choose I. Jm of Jm power I of 0. Then lambda I power L minus I. Okay, this is just the binomial theorem. Now we write out the terms from so if you put I equal to 0, what will you get? So so this lambda I okay, so if you put I equal to 0, this is lambda I power L. So lambda I power L, if you so that is lambda I power L is same as lambda L power I. Okay, and I equal to 0, so this will be identity matrix, and L choose 0 will be 1. So the first term for I equal to 0, this is reduces to lambda L power I. Then for L equal to 1, we get lambda choose L choose 1, lambda power L minus 1 times Jm of 0, etc. etc. So now if you look at this as a matrix, note that this Jm of 0 is a Jordan block, corresponds to 0. Jm square of 0 will be the square of this block. So here all the super diagonals will be 1. Here the ones will be in the diagonal next to the super diagonal. So again in the all the higher powers, these ones are going to move above and above and above, right? So like so this is a diagonal matrix. In this matrix entries will be in the super diagonal. Here entries will be in the diagonal next to the super diagonal. So at each step the each of these matrices have entries in the different diagonals. Okay, so what happens is when you sum all these matrices, this is the diagonal entry. This value will come in the diagonal next to the main diagonal. This value come in the diagonal next to the diagonal, and so on. Okay, because when you sum, note that this matrix and this matrix, they have non-zero entries in the different places. Here one occurs only in the super diagonal. Here one occurs only in the diagonal next to the super diagonal. So when you add them, if you add these two matrices, the entries will be in diagonal, so sorry, in super diagonal as well as in the next diagonal. So when you add all them, you get entries everywhere. Okay, up to this j m power L of 0. So that is our observation. Note that this is a upper triangular matrix whose diagonal entries are non-zero. Therefore, this matrix is determinant non-zero. This means that this is an invertible matrix. Okay, in particular, if you calculate the powers of Jordan blocks corresponds to non-zero eigenvalue, then the nullity is not going to increase. Okay, the nullity going to remain same. Okay, note that if lambda not equal to 0, this is invertible. Therefore, nullity is 0. Again, it's all the powers will also has nullity 0. So therefore nullity is not going to change for arbitrary, it's not going to change for non-zero uh, non-zero eigenvalues Jordan blocks. Okay, now we look at an arbitrary matrix A. So it will have suppose Jordan blocks J0 of sorry Jn1 of 0, etc. etc. Jnk of 0, then Jp1 of lambda 1, etc. etc. Jpl of some lambda L. Okay. So in an arbitrary matrix, some blocks will be 0 blocks. Some blocks will correspond to non-zero blocks. So when you calculate the powers of this matrix, so this blocks corresponds to non-zero eigenvalues going to remains So this each of them will have nullity 0 because each of them are invertible. So its powers will also remains invertible. That's what we just observed. Therefore, only we have to look at the powers of the blocks corresponds to 0. So nullity of A will be nullity of A square will be again nullity of A plus number of blocks corresponds to 0 whose size is at least 2. Okay. So even for arbitrary matrices, whatever we have proved above, that nullity of A square equal to nullity of A plus number of Jordan blocks of corresponds to 0 of size at least 2 hold true. Okay. Not necessarily for nilpotent matrix, for even for arbitrary matrices we can argue like this. Okay. So nullity of A plus uh, cardinality of 1 less than or equal to ni less than or equal to k, 1 less than or equal to I less than or equal to k, such that ni is greater than or equal to 2. So from here I am looking at how many numbers are there of size at least 2. So each of them will give me one more nullity to A. So therefore nullity of A square will be nullity of A plus this quantity. So these blocks are all invertible and it's going to be remains invertible. So these will not contribute anything to uh, nullity of A square. So please, if you can't understand what is happening here, please check what is Jordan canonical form in my videos. Then it will make much better sense. So this is very important concept. Like this time they ask for nilpotent, next time they ask for arbitrary matrix. So please have a look uh, at the about Jordan canonical form. Okay, guys. So if you learned something new in this video, please click the like button and share with your friends and subscribe to my channel. Thank you.